Hi, good morning. This is a video log entry 164. It's about 10 a.m. CST. Got up at around the same time as usual. I was just doing a little bit of research and I was just reading, I guess. And I was looking at that blog again when it comes to computer architecture and actually understanding how programs work when it comes to the registers and just a very abstract view of like how the CPU works when a program is being executed and whatnot. They call it like a fetch execute process, and it's fetching from a particular section in the program after the binary is made. It has like a read-only section, and part of that read-only section is the underscore with a dot text, which actually contains the code for the execution. And of course, you can look at all of the. You can actually, I think you can basically look at most of the information when you do an ops dump of the ELF with a binary. ELF is executable in linkable format and whatnot. And I was just reading into that a bit, and I was looking back at my video from yesterday, and I was wrong about the origin of x86-64. Actually, AMD was the one to create that architecture. They had originally x86, which was 32 bits, and then they went to x86-64, which means that they could have more complex instructions. That's why they came up with a complex instruction set computer, and these instructions can do multiple operations in one go, I guess. I don't know. And yeah, so it's apparently it has a more extendable format, and I don't know. They say it's useful to a degree, and of course it's useful. We still use it nowadays, and they're using legacy systems because AMD has been around for a while, and actually Intel came around to implement the x86-64 architecture, and they called it Intel 64, and I wasn't aware of that. So now I know, and I don't like spreading misinformation. I just hope that people actually look online when I say this kind of stuff, and I'm sure they do. They don't, obviously. Most people, they like to, what do they call it, fact check. So nowadays especially, and I don't know, I say nowadays especially, but people are smart because this is the information era. You'd expect people to be somewhat smart when it comes to information. So yeah, I was looking at that, and I don't know, I kind of like, they just had a lot of things. I don't know, I just got into a Wikipedia page and I was reading about it, and it was the Wikipedia page, it's just called x86 because it's still the same architecture, but it went from 32. The 32-bit system was actually, the reason why it went from 32 to 64 is because, well, the instructions are larger, right? Because it requires more information, so that's why 60 went from 32 to 64, and it's also still backwards compatible, so you can still run 32-bit programs with the x86-64 architecture. So that was interesting to see and whatnot. And of course, I mean, like, what if you look at Windows? Of course, you have your 32-bit systems and 64-bit systems, which are still using I think most computers use that architecture. So as opposed to ARM, I think ARM just. Did I talk about this? I think ARM uses RISC, right? I think they still RISC V. I think that's what they call it. RISC V. I don't know what that means. But yeah, so. Yeah, and anyways, yeah, so I was looking at that, and I was just kind of reading about that. I obviously didn't understand like a good chunk of it because, again, I now I feel more incentivized to actually read something or get a book on, computer architecture, and there was a book called Computer Architecture, of course, a Quantitative Approach. That's good. So it's mainly just design of general. They're probably gonna look at the history, and they're gonna go into AMD, and probably like there was probably a monopoly between AMD and Intel, and they had some kind of race in the computing market of some sorts, and I don't really know. So I'm probably gonna read more about that because I feel like understanding that more. And they had something called advanced vector extensions, and I was just writing random stuff. I was like, I don't know what that means. I'll look into that later. And SIMD registers, and I don't know what that is either. I don't know. They were talking about like what. I was also looking at sim registers, and these sim registers actually are 120 bits as opposed to 256 bits, which is 2 to the power of 7, I believe. And I was wondering, it's like, why is it 120 versus? I don't know. I think that was just a hardware limitation, so they couldn't do 256 bits for whatever reason. I don't know. That's beyond me. But yeah, so they eventually extended to 256 bits due to an implementation of AVX, which I said before is Advanced Vector Extensions, and I have no idea what that means. And yeah, that's just like way beyond my depth. But I'm still gonna like kind of dabble and read stuff about that. Although, yeah. And I was just talking about backwards compatibility, optimization, and customization stuff, and all that. So I'm going to read about that before I say anything about it, because I have no idea what any of that is. And yeah, and I also want to get a book on compilers. I don't know what kind of book I want yet, but I know there's a. Let's see what Perplexity says about that. Books on compiler, maybe compiler design. I think that was, yeah, the one from Andrew Apple is the most common one. It's Modern Compiler Implementation. What's ML? Machine language, I don't know. So yeah, I'll probably look at that one. Or oh, so there's one for self-study. Since I consider myself to be an autodidact, I'd probably get the one that's recommended for self-study. Consider more approachable than... Oh, yeah, they also have the Dragon book, which I've heard of before. It's like the de facto book on compiler design, so I don't know, maybe I'll look at that too. But yeah, the biggest one is apparently crafting interpreters, which is... provides a hands-on approach for building interpreters. Let me look at that. Yeah, I don't know. That's something I may look at later. So I'm gonna write some notes on that and write a list of books that seem interesting, and then look at Amazon and see if I can afford them, or I'll check the library to see if I can read some more about that kind of stuff, because it seems interesting. Yeah, so aside from that, I was also looking at... I don't know, I drank too much coffee this morning, so my brain's kind of not here right now. But yeah, so I was also looking at there are like 4 main registers. You have the RBP, which is the base pointer register. You have the RSP, which is the stack pointer register. You have the information pointer register as well. That's RAP. And then you have a linker register. I think they call it that. And it's commonly seen as R14 on x86-64 systems. If you're reading assembly code, you'll see that a lot there. The parentheses imply that the CPU is modifying the information within registers, particular registers. So you have to, yeah. So I mean, it's just like standard assembly code stuff. And so yeah, I was reading into that, and I was looking at like, the dynamics between at least the RBP and the RSP. And, if you have the RSP, if you have initialization of like main and whatnot, the RSP would, the RSP starts at whatever initialization point of memory is for that particular virtual memory. So then it first starts off with RSP being, the entry point, which is main. So it's going to be... I don't know how they do this exactly, but it's probably the base. There's a base, and you have the base pointer pointing at the actual segment of memory before the first variable initialization, plus all the other variable initializations, which are different types and sizes, and you sum all them up, and then the RSP would be RBP plus that given summation of variable initializations of particular size and whatnot, which then gives us the offset of RBP to be RSP, which is the end of the stack at that given time. And what that does is it just tells the computer this is the memory, this is as far as it can go when it comes to virtual memory at that given time, and it can't go further than that. So until a function is called. And what happens is when a function is called, what happens is actually the RBP becomes the RSP because that becomes a new base for that frame because it's adding a new section of stack, and then the RSP is then subtracted by a certain amount, which is a new summation of variable initializations, and that becomes a new RSP. Which is interesting. That's for one layer though. It gets more complicated, and also I forgot to talk about the linker register. The linker register, which is R14, actually takes. I believe what happens is when there's a function call, it looks at the next, because in memory you have a segment, or I guess a sequence of instructions, and then at that function call, LR looks at the next function call in memory, and it takes that particular segment of memory and stores it as addressed in hex. So then LR contains that next I guess instruction call or instruction. So at least when that was what I mentioned before was all under a ASM instruction called push, I believe. It goes through all of that. It contains, so basically push contains RBP changing to the stack pointer, and then the stack pointer being offsetted by a certain amount, and also LR being initialized with the next instruction call before the stack, or before that, or after that call, and just so it knows where to go after it quote unquote pops. And then the pop instruction basically does the inverse of that. So RSP becomes RBP again, and RBP becomes that offset of variable initializations back to what it was before the main function call, or I guess after the function call, because that's when it actually initializes everything. So it goes back to that state and whatnot, and that's what pop basically does. And when you look at multiple nested calls, it gets a bit more complicated because LR can only contain one address, meaning you would actually, when you're on a layer above main and you call another function, LR is actually going to put that address in the stack. I don't know where exactly, I'm assuming it's at the top of the stack or at the bottom of the stack during that initialization, which is still push, but also, I don't know, maybe it's a different kind of push function because it's doing a different set of operations. So it adds that on the top of the stack, and then it has a bunch of variable initializations like it did before, and then the stack pointer is the same thing, where, well, of course, the base pointer becomes the stack pointer first, and then it becomes that offset between RBP plus the initialization plus the address of the linker register, that however much memory that takes. And that's how it basically goes back to the function call beforehand and whatnot. So then and then the LR becomes the new return. So I don't know where exactly the linker register actually stores that information. You would think it would be, I would at least think that it would, the linker register would then take that information for main. I think it would be at the bottom of the stack. It would have to be at the bottom of that, not the bottom of the stack, but the bottom of that frame. So that's what it seems like it would do. So I didn't read into them, just using my imagination. But yeah, so that's basically what happens. So when you pop back, it'll look, the LR would take that address from the bottom of that frame, and then does a standard manipulation for the stack pointer to be the new address location, and then the base pointer to go back to what it was originally, using that offset. It contains, I don't know where they store that offset, but it's in one of the registers. And yeah, and then the linker register will then contain the address of where that next address was before that other call. So, and then it goes back, and then it starts executing back in main. Also, there's more functions to call in the first layer, which is fine too, because the LR has that information too. So then it calls, it starts executing on those functions after that pop instruction. So, and then so that's another interesting thing, is that LR would then first tell it to execute, and then start executing the next, or that first layer, or the layer before that other function call, and then it would then take that address at the bottom of the frame, and then it'll hold it there until it has to go back to main. So that seems reasonable. I'm really bad at explaining things, but yeah, I'm just trying to get myself to understand it more. So yeah, I'm going to read more about the stack because it seems interesting. The program stack is cool, I guess. So yeah, I covered all the big registers, and then there are a bunch of other general purpose registers that hold information for general manipulation of variables. You know, if you add like a certain, I don't know, if you have an integer variable and the computer needs to add 2 to it, then it would take that, it would go to that address, it would reference it, I guess, I think it's a reference, and then it would put it into one of its variables. So it would do an add first. So basically what the add assembly instruction does is it adds a certain amount, and then it moves it to that particular register, and then the register does, and then it does 2 instructions when you modify a variable. It has an add first, and then it does a move. It adds a certain amount to that register. I guess we can call like I think there's like an EAX or something. I guess that's a general register. So it'll add a number to that given hexadecimal representation, and then it would be migrated to EAX, and then it would do another assembly instruction, which does a move. So it moves from, it takes whatever's in EAX after it was modified, and then it moves into that particular section of memory where the variable is stored, and that's how it's modified, essentially. So yeah, so it's actually, for C it's 1 instruction, but for assembly it's 2 instructions. You have an add and then a move. And it's the same thing for subtraction and all the other ALU instructions, arithmetic and logic instructions. So yeah, it's interesting. I just it's a lot to read. And yeah, it seems fun though. How long have I been talking about this? I may have been going off on a tangent here. Oh geez. Oh, it's been 18 minutes already. Wow. Yeah, so I think that's really all I have to talk about, and I'll probably just keep reading about computers, I guess. And I'll be messing around with my game tomorrow, because I actually added a deadline for collision management. That's tomorrow. That's something I have to do, as opposed to reading about computer architecture and how programs are executed in the CPU. So anyways, hope you guys have a good day. Bye.